So in this lecture, we are going to see about the Poynting theorem. Okay, so it talks about it's the work energy theorem in electrodynamics, and we'll see about that. So first, we'll start with writing out the energy stored in the electromagnetic field. So the energy stored in an electric field is given by this formula. Here you have see the expression where I'm pointing out the arrow is given by this formula, and the energy stored in the magnetic field is given by this formula. We had derived this earlier. Now, so if you add them up, you'll get the energy stored in the electromagnetic field per unit volume. Now, here we are doing a integral over all of in the entire. We are integrating with respect to volume. So you remove that integral, you'll get the expression for per unit volume. Then what we do is we take some amount of charge and calculate the work done on them by these electromagnetic fields. So the force, what is the general formula for work done? It is force into distance, right? So F dot dl is the work done formula. Now the force is the Lorentz force. It is the contribution due to the electric field QE and the Lorentz force, which is Q V cross B, right? So electric and magnetic field contribution dot VDT. Now here you can see that V can be written as dl by dt. So from that we get for dl vdt. Now this simplifies to qe dot vdt because magnetic forces do no work, because the direction of motion is always perpendicular to the direction of the magnetic force, so they do no work on here. So you drop that term. Now then what we do is this q we can replace by the charge density multiplied by the volume element d tau, right? Because this is the volume charge density, and you multiply it by the volume element, you'll get the charge. And this, now if you do that replacement here, you will make that substitution here, and you'll have a term rho v. Okay, that rho v we write as j. Okay, why we do how that formula comes is, I'll just show you here. Now if you are supposing have some, you have now rho, the charge can be written out as, you can write out the charge as rho q is equal to rho into a into L. I am writing out the area like this. Okay, the volume like this. The area into the length. Okay, so yeah, I'm V the volume. I'm writing it out like this. Okay, because if you take like a cube like this, if you take a wire like this, which is having this kind of shape, now you can find out, you take a cubical wire, the area into length will give you the volume. So the charge flowing in it, rho, the q is equal to rho into a into L. Okay, so now what I want to do is I divide it by T. So what I'll have here is, in the left hand side I'll have current, right? Q by T is current, and here in the right hand side, now L by T, you know, is nothing but velocity, right? So rho into a into velocity. Now what I can do is I can take the I by a to the left hand side. Now I by a is nothing but j, it's the current density. I by a is the current density, volume current density. So rho into v. So we get this formula, rho v is equal to, let me write out here, so rho v is equal to j. So that's how we get this formula. So we substitute all of that here, and what we get here is the resulting expression here. Let me give the pointer tool. So we get this resulting expression. Now here we had calculated, when you substitute it here, we have to, what we do is we take the time derivative of this term. So when you take the time derivative and of both sides, you're just taking this dt to the left hand side. Okay, you're just taking the dt to the left hand side, and you get this term e dot j uh, d tau integral v, and you get dw by dt. So dw by dt is the rate at which work is done, right? Now let's solve for the right hand side. What is e dot j? Okay, so this e dot j, when we solve, we keep e as it is and substitute for j from Ampere's law. So Ampere's law says that, so you would know Ampere's law, del cross b is equal to mu naught j plus mu naught epsilon naught dE by dt, right? This is Ampere's law. So from this we just get an expression for j and we substitute it here. Okay, we substitute it here. So when I do that, I will get this expression. And then from the product rule, the divergence of, from the product rule, we, this is a vector identity. From the product rule, this we solve for. So from the product rule, we solve for del cross p. So this is the entire product rule. Now just two vectors here, in this case e and b. So we just we have del cross b here. So we write we write an expression for del cross b and substitute it here. And for del cross E, we use Faraday's law. Del cross E is minus dB by dt. This is Faraday's law. So when you do all of that, you get this term. So for E dot del cross B, you have this expression. And B dot dB by dt is nothing but half dB square by dt. Because when you integrate this term once, you will get this term back. Okay, you will get this expression back. So we write it like that. So similarly here e dot dB by dt is half d e square by dt. Okay, so this is also the same way. If you integrate this term partially with respect to t, you will get this term back, this expression back. So we now have all this information. Now we substitute for e dot j. Okay, so all these values we put it in here. Okay, for all these values we put it in here, and we, for all these expressions we put it in here, and we get this formula for e dot j. Now this e dot j has to be substituted here. So when you substitute it here, let's see what we get. So this is what you get. Okay, so you have now got an expression where the first term on the, this is the first term, the integral, first integral on the right is the total energy stored in the field. So if you to leave out this dt inside this integral, if you see, this is the total energy stored in the field. And the second term evidently represents the rate at which energy is transported out of V across its boundary surface. So this term talks about how much energy is going out of the surface S. Okay, and so now the Poynting theorem reads that the work done on the charges, right? So here we are doing, this is the, as I told you, this is the work energy theorem. So you can see what the Poynting theorem means. The work done on the charges by the electromagnetic force is equal to the decrease in the energy remaining in the field. So here you can see that the negative sign indicates that the energy is decreasing, decrease in energy remaining in the fields. Less than, so again you have a minus sign, so less than the energy that flowed out through the surface. So from this surface some energy is flowing out, that is the Poynting vector. Okay, so this E cross B by 1 by nu naught is the energy per unit time per unit area transported by the field, and it is called the Poynting vector.